Well, good morning, everybody. And I want to thank the organizing committee for inviting me here. I'm incredibly pleased to be here. I'm also very, very honored to be given this first opening speech here on Alex's Symposium, where we really celebrate his scientific life. Well, basically, the organizing committee asked me to summarize in less than 45 minutes all of Dalgarno's legacies in astrochemistry. And given the enormous diversity of objects that we have in the universe in which astrochemistry plays a role, you see here a number of them going from comets to clouds, to galaxies, to supernova remnants. All of these areas in their great diversity is what Alex has contributed to. And so it's clearly impossible for me to summarize all of that. And in fact, you'll hear more of it in the subsequent talks and also in the subsequent days. But just as Bill said, to me really what Alex's contributions are is that he brought indeed this rationale to studying all of these objects. He really understood that it's the basic processes that's in these different environments which are actually not that different and which involve the same molecules, the same processes, etc. And so when Alex actually made the switch from aeronomy to astrophysics some 40 years ago, he said basically, well, astrophysics is almost entirely applied AMO physics. And I think that is a statement that we'll see throughout these 3 days. In fact, Alex summarized a lot of that in his recent preface for the annual reviews of astronomy and astrophysics, which is now online and which I can highly recommend to you. So what is astrochemistry? Well, these are two of the definitions that Alex gave. The first one is a more formal one: formation, destruction, excitation of molecules in astronomical environments and their influence on the structure, dynamics, and evolution of astronomical objects. Certainly all true, and this definition already illustrates sort of the two-way street between these two subjects. But I really like the second wording better, which is the blending of astronomy and chemistry, and these days also geology and other disciplines. Physics, of course, also comes in there. The blending of astronomy and chemistry in which each area enriches the other in a mutually stimulating interaction. And I think that is what we really hope to show in these 3 days, that is what is happening. So astrochemistry these days is really very heavily intertwined with two of the major topics in modern astrophysics, namely the formation and existence of exoplanets and also the formation of galaxies at the very highest redshifts. Certainly the discovery of exoplanets some 10 years ago opened up this whole field of exoplanetary studies, in fact very heavily linked with studies of planets in our own atmosphere, in our own solar system, which Alex studied many years ago. And it has really sort of also revived astrochemistry in the sense of linking it with the material from which solar systems are made. The whole life cycle of how molecules go from clouds to disks around young stars in which planets are formed, to new planetary systems, comets, sort of the leftovers from the planet formation process, and then also how they die and return material to the interstellar medium and starting this whole cycle again. A lot of that is basically astrochemistry. We use the molecules as diagnostics of the conditions and the processes, and we really want to know and have an inventory of the material that is present both as gases and as solids as it goes into these forming planetary systems. The second topic is the highest redshift galaxies. And again, it's only about 10 years ago that we made this enormous jump of basically going from astrochemistry at a redshift of 0 to astrochemistry at a redshift of 5, when these submillimeter galaxies were discovered. And in fact, the record holder is still a galaxy at a redshift of 6.4, where both dust has been detected. It's this tiny little blip over here, which is seen in the dust, but which is also seen in the carbon monoxide lines. At least 3 of these lines are detected. But very importantly, now also the carbon plus line is seen. In fact, the carbon plus line, which Alex predicted was going to be one of the major coolants of the diffuse molecular gas. So this shows direct evidence that astrochemistry really started very shortly after the Big Bang and that we can use these molecules not only to study chemistry, but also to use them as tracers really of mass, of dynamics, of temperatures, and also of the star formation rate that is going on in these earliest galaxies, which already have produced a lot of the heavy elements. Now, in all of the astrochemistry, there's really this very close interaction between both the observations at various wavelengths, the models, and the laboratory, where with laboratory I mean both the hardcore experiments in the lab, but also the calculations like what Alex is doing. So obviously models, like models of diffuse clouds, models of shocks or PDRs or of disks, they feed directly into the observations and vice versa. But the heart of the matter is really here in the laboratory, which feeds into both the observations and the models. And that goes way beyond just providing basic spectroscopy and oscillator strengths in order to identify the lines. It's really at the heart of the atomic and molecular physics, the collision rates, the photo rates, various other chemical processes, radiative association, charge exchange, etc., which one really needs to know in order to interpret this very rich array of data that we now have from all of our telescopes. So what I hope to do in these next half hour or so is tell you more about Alex's legacy in all of these areas, which are part of astrochemistry, although obviously I won't be able to touch on all of these different topics, and put them in the light of sort of the most recent developments that are now present in these areas. But the bottom line is indeed that the heart of the matter is here in this in the basic processes work, and that is really the main legacy on which we can still continue to build. Well, let's start with a little bit of history in astrochemistry. One could say that sort of the first ingredients for astrochemistry were with the discoveries of the diffuse interstellar bands, which still remain a mystery today. And that was sort of in the anno Dalgarno, sort of minus 10 years before he was born. Eddington's famous Beckerian lecture, where he talked already about the possibility that there could be molecules in space, was about 2 years before Alex was born. The discovery of the first discovery of the first interstellar molecules, CH plus CN, occurred when Alex was just sort of a teenager. And the first models to try and interpret those simple molecules by Kramers and Tahar and Bates and Spitzers was when Alex was in college working on mathematics largely. It's really with this opening up of the radio wavelengths regime, the detection of ammonia by Townsend's group, and then the development of millimeter astronomy, the whole flood of molecules that then came in the early 1970s, which was when Alex was sort of turning 40 and decided to make the move from physics and aeronomy to astrophysics. And I would say that astrochemistry has never been the same ever since. So actually that period of the early 1970s was a lot of excitement actually going on. There were all the new observational data from the millimeter wavelengths. There was the Copernicus satellite, which provided the UV data. And then there were all of these bright theorists here at Harvard trying to interpret all of those data. And in fact, I think there was a sort of friendly competition going on between sort of the CFA side and the chemistry department, where Alex and his students worked a lot on the diffuse clouds, the clouds where UV is clearly important, where you find mostly the simpler molecules, and which are studied primarily by optical and UV absorption lines, basically passing through the cloud and then providing a spectrum where you can see the fingerprints. And then there are the dense clouds where UV is largely unimportant, and where you find also the more complex molecules, and which are studied primarily by the emission lines of molecules at millimeter wavelengths. And that was basically our chairman, Bill Klemperer, and Eric Herbst, who made great strides in that area. So it was a wonderful time where a lot of activity was going on, and also a lot of interactions and discoveries were being made. As we will see, this statement that diffuse clouds only have simple molecules is not quite true anymore, and that also provides us with one of the puzzles that we have today. But at that time, trying to understand sort of the simple molecules, one of the certainly important contributions was the explanation for CH, which by that time had been known for 30 years, but still no good model in order to interpret it. And it was really John Black and Alex who postulated this rate here, C++ H2 going to CH2+, the radiative association reaction, as the basis for explaining the CH in clouds. In fact, when you read back their paper, it's incredibly modest sort of sentence. We introduce a slight modification of the original scheme of Bates and Spitzer and of Solomon and Klemperer, based upon the assumption that clouds contain significant amounts of molecular hydrogen. And that was, of course, the key to it all, that you shouldn't look only at reactions with atomic hydrogen, but with molecular hydrogen, which made the whole chemistry go there. Actually, they found that they needed a rate coefficient of 10⁻⁵ centimeter cubed per second in order to explain the observations. So this may have been one of the first rate coefficients determined from astronomical observations. But subsequent studies, theoretical by Ian Smith and others, and also Celebratory, have shown that this number is actually pretty close to what it turned out to be eventually. So really providing proof that CH is likely mostly formed through this basic route. And so building on this and other molecules, they put together sort of comprehensive models of these diffuse clouds, which explained quite a lot of the observations. But it was also clear at that time that the models failed in some aspect. And the most obvious failure is the CH+, which you cannot form through this reaction C++ H2 going to CH+, because it's endothermic. And this whole problem of the CH+ has been with us now for something like 70 years, and it's still not fully solved. In fact, the situation has only become more complex with the discovery of other more complex molecules in these very diffuse clouds where UV photons can easily dissociate molecules. This is some beautiful work on millimeter absorption lines in diffuse clouds where you look at the background millimeter source, here by Lucas and Liest, where they find also more complex molecules present there, which the standard models certainly underproduce. And so there's now, if we look at where we stand today with diffuse clouds, there are quite a number of additions to make to these standard models. And in fact, one of Alex's quotes is that failures are often more instructive than successes. And also that is certainly true, and we may actually be learning then something about the environments that these molecules are in. In fact, for the CH+ problem, it's clear that the chemical processes themselves are now so well understood that the problem really must lie in our poor understanding of the physics of the structure of these molecular clouds. And so the presence of weak shocks and turbulence has been suggested, but even there we're still lacking a good quantitative theory in order to make quantitative predictions at the level that we can really trust them. Surface chemistry is also raising its head now a little bit in these diffuse clouds, although at a very low level compared with the ion molecule chemistry, for example, by explaining NH. And also the whole structure in terms of the clumpiness is still something that needs to be understood. But the bottom line is that you can still use these very simple clouds, the diffuse clouds, as one of the best test beds, and we must continue to do that if we really understand our basic foundation of the interstellar chemistry and cloud structure. One important ingredient in all of these models is the cosmic ray ionization rate. And Alex, together with various students, with Tom Gravens and also with others, has used, for example, the OH molecule in order to infer values of the cosmic ray ionization rate. More recently, it's really the discovery of H3+ and the direct observations of H3+ that have provided the most direct indications of this rate. First detected through beautiful laboratory and observational work by Oka and Jabol in dense clouds in 1996, and now more recently by McCall and his students in a whole set of diffuse clouds. And these signals are surprisingly strong in these diffuse clouds. The chemistry is very simple. You simply relate the H3+ by the ionization rate, and the main destruction is dissociative recombination. Now, for a long time, we could hide our ignorance in this number because there was quite a bit of discussion in the literature for something like 30 years or so about the value of this rate coefficients. But a whole series of measurements now in storage ring have shown that this rate is really rather rapid. And so that means that all of the ingredients here are either measured or are directly observed, electron density through the carbon plus abundance. And so that means you can directly plug in the numbers and obtain a measurement of the cosmic ray ionization rate. And in fact, the rate is surprisingly large, some 10 to 50 times larger than the canonical value that people had assumed, although some of the early models already had at least some of the higher values in them. And incidentally, also for dark clouds, some rather larger values are being inferred at this time. And so this really brings into question as to, certainly it affects a lot of the subsequent chemistry, and it also brings into question as to, as Alex puts it in a recent review for the National Academy proceedings, the interesting question as to why these numbers are actually so similar rather than different, as one would expect if the propagation of cosmic rays through the interstellar medium can be rather affected by various processes. Okay, moving to the simplest molecule, H2, of course at the heart of much of the chemistry. Here it's really that Alex has provided a lot of the basic data that we still use today in all of our standard models. The whole process of dissociation of H2, the process of absorbing into the Lyman and Werner bands and then radiating down to the ground state and then dissociating, suggested previously by other, but it's really Dalgarno together with his student Stevens from physics who managed to calculate this process properly. And in fact, it sounded like a lot of fun to me that once they calculated the spectrum, then also in comparison with experiments from Hertzberg, it turned out that the emission was indeed very well reproduced. And in fact, this whole sort of UV fluorescence spectrum from molecular hydrogen, consisting both of lines and of this continuum, continues to play a very important role these days also in the chemistry, not just by UV excitation, but also by cosmic ray ionization, and then the secondary electron basically as exciting the molecular hydrogen. A very nice work of Emil Sternberg and Roland Gredel have provided sort of the basic rates for these processes that still continue to be used today in all of the astrochemical models. That, of course, also involved getting a lot of the basic cross-sections for photo processes assembled, and certainly Kate and Wayne Roberge and myself have contributed to that in a series of papers. Well, about 10% of the absorptions into the excited states of H2 result in dissociation. The remaining 90% result in excitation of the H2 molecule. And there, really a whole set of papers and work with various students has contributed enormously to sort of the basic understanding of the molecular hydrogen spectrum. Starting with Black and Dalgarno in the early 1980s to sort of use these excitation as a diagnostic of the physical conditions. And then later with Emil Sternberg looking at the higher density regions, and then subsequently also with Roland Gredel and Tine et al. In the molecular hydrogen exposed to X-rays. And in all of these cases now, the observations actually have become now good enough at infrared wavelengths that these spectra are just directly measured and compared with these models. And in many cases, the agreement is really fantastic. Well, putting all of this into a cloud model is what John Black and Alex did in the early 1970s and the late 1970s. And they showed already the important process of self-shielding, that molecular hydrogen basically lying at the edge of the cloud absorbs all the UV photons so that molecules deeper in the cloud don't see those UV photons anymore. And so you see here, as a function of depth into the cloud, the H2 dissociation decreasing, and also the H2 excitation. Now HD, of course, electronically completely similar to molecular hydrogen, dissociates in the same way, but it cannot shield itself because it is a factor of 10 to the 5 less abundant. And so its dissociation rate stays high throughout the cloud. But at the same time, while it's dissociated much more rapidly, it's also formed much more rapidly through gas phase reactions, starting here with a charge transfer reaction. And so Alex and John realized basically that they could use in this way, if they understood this chemistry well enough, they could use HD in this way in order to determine really the D over H abundance, the cosmic deuterium abundance. And in that way provides another important ingredient for astrophysics. Well, that brings me, H2 and HD really brings me to the very simplest molecules, the molecules that were present already at the beginning of the universe. And in fact, I remember a wonderful lecture by Alex in 1985 in the IU Symposium in Goa, which he started with the dawn of chemistry. And in fact, here you see Alex with Steve Lapp, with whom he was mostly working at the time. In fact, Steve, I have a lot of photos of you together with Alex. You seem to be together in a lot of photos. Here we are on our way from Delhi to Goa with a number of stops, and we are here at Udaipur in Rajasthan. For those of you who don't know Udaipur, it's where this wonderful palace is on a lake. Octopussy and James Bond has her hideout there. In any case, we visited that castles, and that whole trip was actually very, very nice for bringing a lot of us astrochemists together. In any case, Alex gave a wonderful lecture there, showing how the first molecules were formed. These figures are actually from a paper by Letter and Black, but the idea is the same. Once the atoms start to recombine, then the first molecule you form probably in the universe is helium-2+, and shortly thereafter helium-H+, another one of Alex's favorite molecules, unfortunately still not yet seen anywhere in astrophysics. But then once helium is recombined, then it's really when you start to recombine hydrogen into from ionized to neutral form, and that's when you start to make the first molecules. And you start to make it in two routes, where Alex has contributed enormously to our understanding of these processes, both through the H plus radiative plus H radiative association and this H minus plus H associative detachments. In fact, this is a process that Alex studied already in 1954, but at the time of being completely outside astrophysics, he didn't realize the full importance of it, and that was realized only later by other people. But Alex had already provided a rate for it at that time. Well, Alex continued to work on early universe chemistry, later also with Phil Stencil. They worried a lot about lithium hydride at some stage. In fact, together with Kate, they did a lot of basic calculations to get the molecular processes right. But in the end, I think it didn't matter so much. Those of you who have good eyes see that there are 40 orders of magnitude here on this scale. And so lithium hydride is really way down compared with other species. But the other two molecules, H2 and HD, are really very important. And they are important because they are very good coolants of the clouds. Molecular hydrogen down to temperatures of about 100 Kelvin, and HD, even though it has a lower abundance, is important because it can cool to much lower temperatures than molecular hydrogen, so its energy levels are closer together. And so the result is that it really lowers sort of the Jeans masses that you can for collapse on the formation of the first stars and galaxies. And so this is from the very famous review paper of Dalgarno and Dick McRae, where they already calculated all of these cooling rates. And incidentally, they also pointed out the importance of the carbon plus cooling for the interstellar medium today. In fact, this whole issue of the formation of the first stars and galaxies was very much alive already at the time of 1985. If you go back to the IU Symposium and you read the discussion after Alex's talk, it's 1.5 pages just about physics of the early universe. And almost nothing about chemistry there. And lots of questions about what kind of objects you form, what size of objects you form, and Alex's comments already about that. Interestingly, there's also a question here in the scenario of the formation of protogalaxies you presented. Will it be possible to observe the redshifted H21 centimeter hydrogen line? Alex says, I think not, negligible. Of course, this is now one of the main drivers for many of the more modern telescopes that are being built, the pre-SKA, LOFAR, and the Australia projects, and of course the SKA project itself. So it might be useful to go back to that calculation and double check. Well, here's just an example of how all of this basic information about these processes is now being incorporated into simulations of the formation of the first stars and galaxies. Here, a simulation by Tom Bell et al., another set by Volker Brom et al. Of course, a lot of work going on here at Harvard as well. But the main conclusion now seems to be that basically one forms sort of these first objects with typical masses of about 1,000 solar masses, which then start to collapse to form stars, which are somewhere between, say, 30 and 100 solar masses. Okay, back from the early universe to the current universe, H2D+. What I didn't know until I started preparing this lecture was that Alex was actually the first one to calculate the spectrum of H2D+ in 1973. Clearly a very busy time those years. In fact, his frequency for the line that we can observe from the ground was 344 gigahertz. Not too close, but also not too far from what we know it is, about 372 gigahertz. Well, H2D+, like H3+, is a very important molecule in the chemistry, and it drives a lot of the deuteration. It was finally detected in 1999 in a cold dark cloud. People had previously been looking at somewhat warmer regions because it's an excited line and you need some excitation for it. But in the end, the line turned out to be strongest here in these very cold cores, these dense clouds, in which we know actually that a lot of the molecules are frozen out until on the grain surfaces. In fact, H2D+ has now been detected in these clouds. Even D2H+ has been detected. And highly deuterated molecules, not just singly deuterated, but even triply deuterated molecules like ND3. So there's a whole industry just in the last 5 years of finding these multiply deuterated molecules in these very cold clouds. And it's all driven through this H2D+ ion. Basically, the forward reaction here going very fast at low temperatures, but also the fact that both H3+ and H2D+ are enormously enhanced when their main destroyers, namely carbon monoxide and N2, are frozen out onto the grains. And that's one of the other main developments that we now have in astrochemistry. We know that in these cold dark clouds, most of the heavy elements are actually frozen out onto the grains. And that's responsible really for this enormous deuterium fractionation. You can use it to infer also the ionization fraction, something that Alex has been interested in for a long time, and find values of it that are important, obviously, in the dynamics of these clouds. Well, we've been talking a lot about positive ions. We now know that there are also negative ions here in these clouds. In fact, Alex started thinking about negative ions already in the 1970s with Dick McRae. Certainly others like Eric Herbst were thinking about it. Together with Steve Lapp, we studied the chemistry of negative pHs, or larger molecules. We were not allowed to call them pHs at the time because the identification was too uncertain. But I think later we switched back to pHs again. But it is really the realization that it's the carbon change, which can very easily be negatively charged because of their huge electron affinity, that have become now a subject of very intense study. And it's the beautiful work of Pat Thaddeus and Mike McCarthy and their group that finally identified these molecules first in the laboratory and then in interstellar space. And there's now a whole very active research going on all of these negative ions in space. Okay, well, moving from the cold clouds to the somewhat warmer clouds, the PDRs and the shocks that we're going to talk out here are two of Alex's hot guys. Emil Sternberg and David Neufeld here 2 years ago at the Nobel Symposium in Sweden. And they were both present in the late 1980s at Harvard when I was there as well. And it was a very exciting time because a lot was happening there in that time in our understanding of these regions. PDRs are clouds that are exposed to intense UV radiation, like, for example, one of these bright stars that you see here in Orion, and, for example, the Horsehead Nebula. Emil will probably talk more about this later in the week, but one of the predictions they had was that there was this warm, very warm layer at the edge of these very dense PDRs, where the temperatures were high enough to drive a lot of the endothermic reactions that normally don't go in cold clouds. And that gave some unique diagnostics, like, for example, the CH plus and the CO plus, which was subsequently indeed also detected. Alex and his students, Steve Lapp and also Min Yan, not only studied UV photons, but also the X-rays incident on these clouds, and they wrote a very nice set of papers there, pointing out several X-ray diagnostics like HCN, NO, etc. And in fact, they made very good use of Alex's knowledge of ionized regions in the work that he did with Scott Butler and Tim Heil in the early 1980s on the charge transfer of these doubly ionized ions, which obviously he also gets with the X-rays. In fact, X-rays are now very much a part of interstellar chemistry. Just in the last few years, there has been enormous activity, both in the area of young stars, young stellar objects, and pre-main sequence stars with disk, which are known to emit strong X-rays. And in fact, one of the diagnostics here, the NEAL2 line at 12.2 micron, is now seen in quite a number of disks. Also in galactic nuclei, the whole question of whether they are powered by AGNs or by starburst is very much a question as to whether your molecular gas is irradiated by UV or by X-rays. And here again, there's now a whole set of models being developed in order to test that. Shocks and outflows, obviously also high temperature regions in the interstellar medium. This is a very nice sort of image from both Spitzer and in optical blinking through the Spitzer image, which is the green-bluish one, and the optical image, which is the brownish one, where of a star-forming region here in Perseus. You see beautifully how you really need the long wavelengths in order to penetrate into these dusty clouds, and then see all of these sort of green things here, these green fuzzies emerging, which are all shocks into the interstellar medium. And Alex studied that with quite a number of students. Of course, the beautiful work he did with Bruce Grain and Wayne Roberge on the Ctype shocks, where they showed that really chemically what they're doing is transforming a lot of the oxygen into water. And subsequently with David Neufeld, he studied the more dissociative, the faster dissociative shocks, and in a beautiful paper in 1989. And again, a lot of that was confirmed several years later, both with the ISO satellites and also with the SWOS satellites, which was able to observe the water lines and also spectrally resolve the lines and really show that most of the oxygen was driven into water in these regions. And I suspect that David will talk more about how nowadays with Spitzer we are seeing water basically in many of these young stellar objects here. One of these objects here in NGC 1333 in a beautiful Nature paper here, the mid-infrared spectrum. Most of these lines are actually water lines, probably due to the shock in the region. I would like to end by going to a part of astrochemistry in which Alex hasn't played such a major role yet, and that is solid-state astrochemistry. We now know that, in fact it has been known for quite some time, that the grains in the cold clouds obviously accrete layers of ice. They act as a deep freeze on which the molecules can basically freeze out, and then a lot of chemistry can occur on the grains. And there are very good reasons to stay away from this kind of chemistry, because it's a lot more dirty than the gas-phase chemistry, and it's much more difficult to isolate sort of one process that is really important. But in the last sort of 5 to 10 years, there has been quite a revival of this chemistry, because a lot of very good surface scientists, surface chemists, have sort of turned their experiments into experiments that are also useful for astrochemical purposes, and they are now providing really good basic insight into solid-state processes that occur, processes involving also simple ices where you can understand a lot. And all of that chemistry is now very relevant for the study of the formation of stars and galaxies, because they occur in dense cold regions where the molecules are actually frozen out onto the grains. This is a nice movie here where we show basically how you go from a cold cloud here at optical wavelengths to the infrared wavelengths region, and it's only at the longer wavelengths that you really see that these young stars are being born in these clouds, and they have here a bipolar outflow trying to blow away the surroundings. Now, when you take an infrared spectrum towards one of these objects, here's the same object, take an infrared spectrum, and what do you see? You see a whole fingerprint of ices there. Very simple ices like water, CO2, CH4, etc., together with the silicate cores. But if you look carefully, also here in the silicate bands, there's now also very strong indications for methanol and ammonia in large amounts being present on these grains. And in fact, once these grains are heated, then they start evaporating their molecules back into the gas, and that's what we're now observing, not just in high mass star-forming regions, but also in the lower mass star-forming regions where stars like our sun are being formed. We see a lot of complex organic molecules there, not just methanol, hot methanol, but we're also starting to see there even complex organics like dimethyl ether, methyl formate, etc., showing that even sun-like stars, when they're young, have a very complex chemistry. And it's really the solid-state chemistry that probably explains most of that. And so that's why a lot of experiments are now trying to sort of simulate these processes that we think are happening on the grains in the laboratory under very laboratory-controlled conditions. And this is just one example to showing, this case from our laboratory in Leiden, how you actually can make alcohol in the ices at very low temperatures, starting from simple molecules. Also, molecular dynamics studies in molecular physics have developed to the point that they can be applied to study interstellar ices, and there are various groups now active in that area. One very basic process is what does UV radiation do with an ice? What does it do with a water ice? Well, it obviously dissociates the molecules, but it also can kick out molecules. It can photodesorb the molecules. And these are some nice simulations here showing how this can happen, and also at the same time making quantitative predictions for how this can happen. All of this is very much needed if we want to study the chemistry of protoplanetary disks, where planets are at the moment formed. Because the molecules that we may be seeing in these disks may well be the molecules that we get off the grains through either thermal heating or this photodesorption process. And one of the big questions is really for the future is how much water and how much organic is there in these disks, and where is it located? And with the very recent observations with the Spitzer Space Telescope, we are actually starting to detect some of these organics now in just the inner few astronomical units. We see high abundances of acetylene and hydrogen cyanide, molecules that we need in order to build complex organics, orders of magnitudes more than in disks. And we even, in just a few months ago, two groups by Kara Najita and Caltech by Selek et al. Have discovered also very strong lines of water from these disks. And this, we first thought that this was noise, but it wasn't noise. It was all water lines, the mid-infrared spectrum of hot water. Or telling us that there is a lot of hot water in the planet-forming zones of disks, which again is important for how we form planets. And in fact, even the planetary atmospheres themselves are being studied now. The Spitzer Space Telescope has been able to make the first spectra, infrared spectra of molecules in these objects, and finding evidence for water in at least one of these exoplanetary atmospheres. And so this is an area that really will bring astrochemistry and aeronomy, one of Alex's starting points, together again, and it should be a very exciting area. So I then want to end with the question that Alex actually posed in 1986, and namely, is astrochemistry useful? Alex at that time was a little bit hesitant. If you look back at his paper, then it was sort of a bit from grumbling that we're not doing as well as we should do, maybe. But I think in the last 20 years, we have come to age, and we've really shown the importance of astrochemistry in the whole diversity of astrophysical problems, both in terms of physical diagnostics, of coolants of the early universe, of chemical diagnostics, and also the chemical composition then from which our new stars and planets are made. And so it's really true that astrochemistry is now an integral part of modern astronomy. However, I hope that has been clear that it can only thrive by close interaction with the neighboring fields, particularly chemistry and physics. And I think that also makes it very interesting. It makes it highly rewarding intellectually. In fact, I enjoy myself always most if we understand the basic process again. And it's sometimes much more challenging than just turning the knob on a model, which only includes a number of numbers. So I think it's also very worthwhile in that respect. Well, one of the reasons that astrochemistry has become so prominent is because Alex recognized the importance in astronomy and established an IAU working group on astrochemistry. And that working group has been active in holding a number of IAU symposia, which as their basis really have a very broad coverage of all the aspects of astrochemistry, not just a small part, but really all of the aspects of astrochemistry, including also the physics and the chemistry, the basic processes. We started in 1985 in Goa, then Brazil, then Leiden, then Korea, Asilomar a few years ago, and we're planning for our next one in a few years from now again in Europe. And here you see Alex actively interacting with various participants here, both in the Leiden and the Korea meeting. I think the future of astrochemistry is bright. Many of the new and exciting facilities that are being built today are perfectly suited. I mean, they're basically dream instruments for astrochemistry. Herschel, which will be launched next year, ALMA, which is coming online in the next few years, SOFIA, which will start to make its first flights next year, JWST, which will come around 2013, 2014. The extremely large optical telescopes, they all will be equipped with high-resolution spectrometers, which can then do a lot of astrochemistry. And so these molecular observations will clearly be happening, and you need then a lot of people who actually know how to interpret these molecular data. And that's really where the complementary laboratory data, that sort of third pillar of the whole interpretation of the molecular data, becomes so important. And so that's why we really need this sort of well-trained young astrochemist or molecular astrophysics who also know their basic atomic and molecular processes. In fact, it was Henk van der Hulst who said, who sort of accused cosmologists some time ago that they were playing tennis without a net, when they were basically just putting forward model after model without any data to constrain them. Well, if we didn't have the basic laboratory, if we didn't have the basic atomic and molecular physics data, we would be playing tennis without a net. And Alex made sure that we're always playing tennis with a net. And so Alex's legacy is basically us here in this room who have been trained in these atomic and molecular physics and who can hopefully transmit that to the next generations. So I want to thank Alex for training us and for caring for us so well and for also making sure that astrochemistry is so much fun. Thank you very much.
Are there questions or comments?
Well, it's actually, I mean, yeah, Alex was coming that solid-state astrochemistry was too difficult. But I must say, I mean, I'm a hardcore sort of gas-phase chemist myself, and I was very hesitant ever going into solid-state astrochemistry. And I think Eric may be in the same boat as me. But I must say that both the experiments and the theoretical tools have now gotten to the point that one can actually, if one picks the right problem, one can actually now get real answers to real questions. And I think that's at least the first step in that direction in understanding the solid-state astrochemistry also better.
I'd like to make a hostile remark.
Good.
And I think that the history of astrochemistry starts with nothing but solid-state chemistry.
Yes.
And it really led nowhere.
Well, except for molecular hydrogen. That's
for
molecular hydrogen. Yes.
But that's really astrophysics.
Yes. Yeah, well, I think, no, if you look back, there was a lot of good thoughts that went into a lot of these early models of the chemistry. But it was basically they didn't have enough good hard data to test it against. And that data is only now sort of starting to become available. And that's why we're starting to make progress, but we have sort of 50 years to go before we're anywhere close to what they know in gas phase chemistry.